Hello, in this video we will talk about experiment-wise error rate in ANOVA and using two-case test to dealing with such kind of error. So, in the previous video for ANOVA, we have seen that we can use, for example, confidence interval to test if a single comparison between two treatments' value in experiments. And when we want to make multiple such kind of comparisons between different pairwise treatments' mean value, then the error rate, or we say the family error rate, will increase. So what this mean? So for example, if we set alpha is 0.05 for a single comparison, so which means in this single comparison between treatments group, for example 2 and 5, so we want to make such kind of false rejection or false significance of this pair comparison is 0.05. So we say we have probability of 0.05 such that we will make a wrong rejection if we want to only make single comparison. But if we want to make multiple single comparisons, such kind of error, for at least we will make a wrong rejection for among odd comparisons will be this value. So because this is 1 minus alpha is the probability we do not make false rejection. So the power R is for odd comparisons have no rejection, false rejection, right? So 1 minus this power value will be at least 1 time for the false rejections if we make multiple single comparisons. So one example is if we make six comparisons in the case of 4 means. So there's about 0.26 for at least we will make 1 wrong rejection for these 6 comparisons. So this probability is quite high, right? So you can see this value t half alpha times s and square root 2 divided by n. This is the single comparisons confidence interval for if we plus minus these items to mean difference. So this is a confidence interval for a single comparison if we set the significance level at alpha. And for example, y1, y5 difference, then plus minus this part. If the result covers 0, so we will not reject the hypothesis that these two treatments are the same. If this confidence interval outside of the 0, so we will reject hypothesis that these two are the same, right? So this is for a single, only make a single comparison. But how to deal with the very high family error rate if we make multiple single comparisons? So one way is to use two-case tests. So two-case test is to make the single comparisons more conservative to reject. So what this means? We will make the single comparisons not so easy to reject, because if we have less chance to reject in a single comparison, so we have less chance to make wrong rejection, right? So that means we make each single comparisons false rejections probability is much lower, and then the composite or the family error rate for at least one wrong rejection will be lower too. So if we want to make the family rejection rate, error rate is 0.05, then for a single comparison will be much more conservative than the previous pages, one single comparison. So in place of the factors we show in the previous pages, Tukey's test use this factor Q alpha KV instead. And this factor can be found from the Tukey's table. So this is Tukey's table with Q 0.05 alpha and K is the treatment groups and V is the degrees of freedom. So next we will show an example. Consider 6 treatments, so 6 groups in one factor, ANOVA, and with 5 observations for each treatment. And S square for the pooled mean square error is about 2.45 with 24 degrees of freedom. And this is the treatment mean value for each group from the lower to the higher value. And from the Tukey's table with alpha level 0.05, we can find this factor is 0.05 and with 6 treatment group and 24 degrees of freedom, this value is 4.37 from the previous Tukey's table. And then we multiply this factor with S square and divided by sample size in each group. So we get this factor was 3.059. So for each pair difference from mean value, if we find this difference exceeding 3.05, then we will say this pair-wise comparison is significant. So in this example, there are about 10 pair-wise are significant. So we say pair-wise comparisons. For this single pair-wise comparisons, 10 pair-wise comparisons are different. And if we do not want Tukey's test, we just use usual single comparisons factor with the t-half alpha times square root of s divided by n. Then it is surely that we will get more different comparisons, more significant comparisons, maybe 12 or maybe 15 pairs. Because now we use a Tukey's test, so this is more conservative and we will usually get less pairs significant in the test. So here we get 10 pairs significant. And there totally for the 6th group, there are 15 comparisons, right? So we get 10 pairs significant using Tukey's test. If we want to control at least one false rejection probability at 0.05 for the family error rate, then we have to use the Tukey's test, use Tukey's factor in confidence interval, right?